Right. So I'm going to first introduce the IBL's sort of what's 10 I think it's 10 specific criteria for including a recording. These are called the rigor criteria. There's an article I provided some resources down here. This is associated with the reproducible EFAS paper. That's a preprint and there's an article here about it. But it's basically a combination of, as Julie was saying, some qualitative, like visual manual inspection of the raw data and some automatically computed metrics. So as far as qualitative metrics go, when you're looking at the raw data, and there's going to be some overlap with Olivier's talk here, the absence of obvious artifacts, we're looking at the dead and noisy channels, which can be sometimes automatically detected, and the motion of the probe. For the entire recording, the overall AP action potential band RMS has to be less than 40 microvolts. That's sort of a rough way of excluding extremely noisy recordings. And then we also want a minimum yield of neurons recovered by the spike sorting algorithm. But I'm going to focus here on a couple of the single unit metrics towards the end of the talk. And we have three currently that we use to include or exclude a particular neuron. So one of them is that the unit isn't too small. So the median amplitude of all the spikes has to be greater than 50 microvolts. One is the noise cutoff metric, which I found is often a little bit counterintuitive. And so I made a few slides that I hope make that a little bit more intuitive to understand how this one works. But it has to do with the assumption of Gaussian distribution of spike amplitudes that Julie was referring to. And then that the spike timings are satisfying biophysical refractory periods. So as we were talking about, if they have unrealistic spacing between the spikes. And I'll also get into that a little bit. So for whole recording metrics, a lot of this was covered by Olivier yesterday, but basically just when you're looking at raw data, comparing good AP band data here, we're seeing that there's not too high of a noise level. The individual spikes are well distinguished when you're visually looking at it. This is from a visualization that Olivier has made, where the red and green dots are spikes from bad and passing units, respectively. And then with critical AP band data, you can see these saturation artifacts that he talked about. There's a much higher level of noise. It's harder to distinguish the individual spikes. Obviously, all these red dots are showing that we have no satisfactory units in this stretch of the recording. This recording also had a lot of noisy channels, but these are masked in this view of the raw data because they've been interpolated. So yeah, I don't want to dwell too long on this because it was covered by Olivier, but good LFP band data, you can sort of see in the region where you'll see spikes in the AP band, there's some activity in the LFP. And then obviously you can get very pathological recordings with a lot of the detector being maxed out, a lot of noisy channels, dead channels, stuff like that. So I thought I'd just sort of visualize what some of the raw data metrics that are saved by IBL really tell you. So over here is the per channel mean RMS, and you can really easily see that that's matching the noisy channels there. It's harder to tell from the RMS where the bad channels are, but you can definitely see where the spiking activity will be based on the magnitude of that. So this is just a list of all the metrics that are automatically computed for raw data. And with the IBL lib Python package, you can compute these on raw recordings. So for single unit metrics, like I discussed, there are three. So the first one I'm not really going to get into because it's quite straightforward. The median spiking amplitude has to be greater than 50 microvolts. The noise cutoff basically ensures a roughly symmetric distribution of the spiking amplitudes and then the refractory period violations. So the way the noise cutoff metric works is that since we expect a roughly symmetric distribution of spiking amplitudes, there might be some issues with that, as Julie alluded to. Um, if there are spikes missed, we'd expect them to be on the lower end of this expected distribution. We'd expect them to be very small spikes. So the way that this metric essentially works is that it compares the tail of the two units distributions and basically says that if this isn't roughly like in the same magnitude band as this, then we've missed some spikes, and so we might not have a full picture of this neuron's activity. So this is kind of a visualization of some real neurons from the IBL data set. So these are some passing ones where we see it's more of a symmetric distributions, and then some failing ones where we see that there's small spikes that have been cut off so that there's a detection problem and we don't want to include that neuron. So the original refractory period violation metric that we were using essentially estimated a rate of violations, so spike spacings that are smaller than the estimated refractory period of the neuron. But there are a couple issues with this. One is that estimating, as we saw with the amplitude cutoff metric, there can often be spikes missing and our detection is imperfect. So estimating the refractory period is error prone. And there's also a bias towards neurons with lower firing rates than the estimated firing rate. And we also saw when we compare I'm not sure why that happened. That's interesting. When we compare the Venn diagram of which units are failing for what reasons, we saw that there are a lot of neurons that were actually losing based on this refractory period metric, and maybe we could recover some units that are being wrongly excluded. So at the last course, Noam Roth discussed a new confidence-based refractory period metric. This is the work of these people right here. So Gael Olivier, Noam Roth, Nick Steinmetz. So because refractory periods vary across the brain, and because computing or estimating the refractory period is error prone, this method actually computes confidence intervals based on Poisson statistics for a grid of potential contamination values and potential refractory periods. And you can set a minimum confidence level that you want to include that neuron. So I just wanted to sort of give an update from that talk that Noam Roth had given. We have computed this metric and applied it to the IBL data sets, and we saw some interesting results, which was that when you plot, make basically a histogram of the units and the confidence for this metric, there's a very interesting distribution where it seems like a lot of neurons fall into either extremely bad or extremely good. And this is a curve of how many units we're able to pass and include as a function of tuning this confidence parameter. So that's just an update on that from the last course. Yeah, thanks.